welcome to DSU 2014, the University of Cape Town, no, beautiful country of South Africa. I hope you had a easy journey down here. Many of you have traveled from all over the world, and it's great to see that many of you have made such a fantastic effort to come here. We've got a packed program. It's a nice blend of theory and observation. We've got several outreach events. In particular, we have a great, very exciting event at UWC on Thursday evening, which I hope all of you will come to. And a nice banquet and tour around the Cape. So I think you'll have a really enjoyable time while you're in Cape Town. And if you've got any questions and anything you want to do outside of the program, please don't hesitate to talk to me or Nikki or Rashada. I'm going to now hand over to the Vice Chancellor of the University, Dr. Max Price, to formally open this conference.
Good morning. Thank you, Peter. Welcome, ladies and gentlemen, scholars, students. A special welcome to Dr. Fanaroff, the Cyclone Project Director of the Square Kilometre Array. The opportunity to host a conference of this scale and magnitude here in the Western Cape, in collaboration with the University of Western Cape, bringing together people from across South Africa, and the continent, really is not only an opportunity we're really proud to take advantage of, but is one that is an activity that symbolizes and represents how astronomy and cosmology works as a science. In other words, its fundamentally collaborative nature, the recognition that this sort of work has to be done by many people working together. It requires collaboration, and for that to really be successful, people need to get to know each other, not just across the internet, not just through the names that appear as authors and co-authors on articles, but through spending time together, working together, getting to know each other, putting a face to the name. And I hope that this conference will therefore contribute significantly, not just in the sharing of science and knowledge, and sharing of creating a consensus or an agreement on what the big questions are and how to approach them, but especially in creating friendships, in creating familiarity, and creating networks. This is, of course, a serious scholarly conference, but I would suggest that it's also a celebration of how the study of the stars has lifted South Africa onto the international stage, and how as a nation we are creating human capacity building a cohort of scientists at the core of an international network of African astronomers, space physicists, citizens, who are all bonded in a common experience, common goals, interlinked professionally and personally, and able to make a contribution to the transformation of society. And I want to say something about that later. Astronomy is a science that spans not only the distance between the planets and the galaxies, the space distance, but also the history of the universe, the time distance, all 14 billion years of it. It has the broadest reach of all the sciences, uniting us in a common endeavor to understand the emergence of life on Earth and this planet's place in the cosmos. Astronomy has deep roots in human civilization. It links all continents to ancestors who gazed up to the night sky and created narratives to explain the movements of heavenly bodies, and who invented the rudimentary disciplines that we use today to measure those bodies and their movements. Astronomy is based on fundamental science and engineering. It has powerful spin-offs in both areas of science and engineering, while also contributing to human understanding and culture. It captures the imagination of the youth and in that way draws them into science. And those trained in astronomy have valuable transferable skills that can contribute to a knowledge-based economy and to the future. So today we can look not only at the past, to past achievements of the science and to the past history of the universe, but also to the future in terms of our aspirations for further understanding and in terms of the kind of contribution that the people trained in these fields can make to a knowledge and science-based economy. This conference, for example, will explore questions around dark energy, which comprises 73% of the energy of the universe, and is responsible for the mysterious force that is speeding up its expansion. To understand the dark side of the universe is therefore one of the key fundamental science questions in physics and cosmology, and it may possibly lead to theories beyond the standard models of particle physics and Big Bang cosmology. Some of humanity's biggest questions in science are being tackled in astronomy, including what is the nature of the Big Bang that formed our universe? How did the first stars and galaxies form, including our own Milky Way galaxy? What is the invisible and yet to be detected dark matter that holds galaxies together? What physics governs variable stars, binary stars, neutron stars, and black holes, including the supermassive black holes at the center of galaxies like the Milky Way? Can we detect and exploit gravitational waves, the ultra-weak ripples in the fabric of space-time, predicted by Einstein to open new vistas on the universe? How did the planets form? How many of them are habitable? And the question that keeps the film industry profitable, is there extraterrestrial life? South African astronomy is increasingly involved in the international effort to tackle all these questions, making contributions that are growing in significance with every passing year. And a conference such as this, located here, helps accelerate that contribution and that involvement. South Africa has all the ingredients to become a world-class player in astronomy. It has a strong tradition and resources in both observation and theory. It has geographical advantage. The southern sky is not available to the northern hemisphere and is best viewed from dark and radio-quiet areas with good infrastructure links. The major host of the Square Kilometre Array, the world's biggest ever astronomy experiment, is in South Africa. The site of SALT, South African Large Telescope, and HESS, giving unique multi-wavelength coverage, is located here. And to the great credit of our government, the Department of Science and Technology, the government policy is one that recognizes the value of astronomy and its spin-offs, and that facilitated the successes of SALT and SKA, which is part of a drive towards a more knowledge-based economy. And I want to just repeat that point because it's no mean feat that in a country where many people would argue that the resources and the focus of research attention should be on bringing water and sanitation to informal settlements, addressing issues of food security, the key developmental issues of a developing economy and of an emerging economy, that the government and the people should have seen the wisdom of taking a really long-term view, of recognizing that we will overcome those issues, but if we get left behind in the process in advancing high-tech and high-level science and technology, if we do not at the same time produce industries and engineers and scientists who can work at the cutting edge of knowledge, we will never be a global economy and globally competitive. And recognizing that it's not just about the specific knowledge that, say, an SKA will produce, but about the hundreds, if not thousands of engineers, computer scientists, technicians, factories, people who will take those skills in a transferable way and plow them into other aspects of the economy. That realization, that foresight, is really remarkable. Beyond the development of science itself, as I was saying, these spin-offs depend on the human capacity and growing that human capacity. So let me say something about that. UCT is the host of the National Astrophysics and Space Science Program, known as NASP. NASP is hosted here, but is a collaborative program with many universities in the country, and aims to empower South African and foreign African students to embark upon postgraduate studies in astrophysics and space physics by providing them with the necessary skills, knowledge, and inspiration. By harnessing national expertise and resources, which any one university might not have, but collaboratively we have, taking advantage also of global networks, NASP is committed to producing honours and master's graduates whose qualifications are internationally competitive. The program promotes diversity and transformation while growing the next generation of graduate astronomers and space physicists who enter and contribute to the South African workforce, where skills in mathematics and physics and a command of research methods are clearly advantageous. Transformation is at the core of NASP's objective to build a fully representative community of astrophysicists, space physicists, technologists, and cosmologists who participate in the South African and Pan-African science enterprise or in other professions that depend on highly skilled and innovative people. Furthermore, NASP nurtures a well-connected community of young scientists who have the opportunity to assume leadership roles in building South African and Pan-African astrophysics, space physics, and cosmology. It's worth reflecting on the last, 12 years of NASP's successes. Over those 12 years, some 160 students have graduated with honours degrees since 2003, and nearly 200 altogether, some still currently registered. And of those 160, 62 were black South Africans, and 64 were other Africans, foreign Africans, from the rest of the continent. So fully 126 of the 160 are black scientists from the continent of Africa. In the master's program, the MSc program, some 102 have graduated during this period, and of those, again, well over 50%, some 73 are black South Africans or black foreign Africans, 25 South African, 48 foreign African. And at the level of PhD, more than 25 PhDs have graduated and 45 are currently studying. This is an element of transformation which affects not only South Africa and Africa, because it produces the quantity of scientists. It affects us not only because it produces the diversity. It changes the way the world thinks about cultural diversity and about race. And in some ways, UCT plays this role in many fields. I want to give you one example from a completely different field, but I think it's analogous. The world has hardly ever seen and does not, and so the stereotype of opera singers being a historically Eurocentric art form or genre is such that the world is unfamiliar with and has not seen black female opera singers and black opera singers who would perform the parts which in European tradition and stereotype could only be performed by a blonde white woman such as Lucia. South Africa's production and UCT's production of black opera singers is changing global perceptions of the art form, of its ownership, and of the kinds of performers that should be performing. It's transforming global perceptions of stereotypes. And I would venture to suggest that the NASP program, and more generally, the transformation programs in science and technology here, achieve the same sorts of goals. That because there are so few black and black African role models leading the science, the stereotypes globally are that black and African scientists do not rise to those levels or do not provide that sort of thought leadership. It's through programs like NASP that we change those perceptions both in the continent and globally. And so it's an impact of transformation which extends way beyond our shores. I want to finally say a word of thanks on behalf of the university to your host, your conference host, the UCT Astrophysics, Cosmology and Gravity Center, a center we're very proud of, established in 2009, with the primary goal of forming a major research hub in those fields, astrophysics, cosmology and gravitation, in Southern Africa, with particular emphasis on projects involving the new facilities of SALT and Meerkat that will require the expertise from both observers and theorists. The center provides a natural home for students and staff of the NASA program. It's a joint venture between the Departments of Mathematics and Applied Mathematics and Astronomy, and highlights the importance of interdisciplinary work at UCT. Its directors are Professor René Kron-Korteweg and Professor Peter Dunsby, and I want to compliment both of them on this on the organisation of this fantastic conference. So on their behalf, and on behalf of the University of Cape Town, it's my honour to welcome you all again and to open this conference and wish you a most fruitful week of deliberations and of fun. Thank you.
Thank you very much, Dr. Price. We have a very distinguished guest with us today, Dr. Bernie Fanaroff. As Mark said, he is the project director of the South African Square Kilometre Array project, but also, I would say, one of South Africa's most illustrious ambassadors of science in general. He's a recipient of one of the highest honours given by the South African presidency, and he's here today to tell us a little bit about the journey towards the SKA and what it hopes to achieve. Thank you very much.
Everybody, can you hear me? Is this thing working?
Yes.
Thank you very much to Peter and Roy and UCT and University of Western Cape for inviting me and to the rest of the organising committee. It's a great pleasure to be able to talk to you about the SKA. Especially nice to see so many students. I see you guys work on cosmic time, so I'll interpret my 30 minutes as being somewhere more than 3 minutes and less than 300 minutes. Just to follow up on what Max Price was saying, there are some nice messages in what he was saying about Cape Town and about the Western Coast. So in February we'll be opening an exhibition at the Ezekiel Museum here in Cape Town of tapestries done by descendants of the Sand people who populated the Karoo and who are some of the earliest modern humans in the world, together with art done on astronomy by the Aboriginal people of the Western Australian outback, where the Western Australian part of the SK will be built. And we've also commissioned a book which is being done by scientists from UCT and BITS on the history of technology. South Africa plays a unique role in that, as being the site of some of the earliest modern humans, but also as being the site of some of the earliest technology, and the booklet will trace the history of technology, some of which is shown in caves near Cape Town, Longboss, Pinnacle Point along the South Cape coast. and take it through all the way to the SKA, which is cutting edge technology. So what we always do when we speak is welcome those of you who weren't born here to South Africa, which is ultimately your ancestral home, so welcome back home to all of you. The last time I had a serious interaction with cosmology was in the early 1970s, and Max referred to the fact that you guys are working on how the Big Bang worked and what it looked like. In the early 1970s, the question was there a Big Bang or not? And those of us who were studying under Martin Ryle in the Cavendish laboratory were not encouraged to go to seminars at the Institute of Astronomy, which was led by Fred Hoyle, because the debate between the steady state and the Big Bang universe was a very personal thing. So you either believed in the Big Bang or you believed in the steady state, but you weren't allowed to cross the road between the two institutes. So things have changed a bit, and I'm always amazed at how you guys have converted what was then really a question of aesthetics as much as anything else into a precision science. So congratulations, but I'm very glad that Roy and Peter didn't ask me to say anything intelligent about cosmology, because you've gone a hell of a long way further than I understood. Max pointed out that the South African government has taken a very progressive position on astronomy, and this is a quote from a white paper, which is a government policy paper published in 1996, 2 years after our first democratic elections, in which government said that we have to respect basic sciences as much as applied sciences, because they're crucial to our development as a nation. We're not a second-class nation. We can compete with anybody in the fundamental sciences. And this has been carried forward since the beginning of the Square Kilometre Array project in South Africa in 2003. And the SKA and the building of our precursor telescope, the Meerkat telescope, are classified as one of the special infrastructure projects which are being driven from the Presidential Infrastructure Coordinating Commission. So this is a picture of the President and our cabinet ministers on the site of our telescope early last year, when we launched the Meerkat and the SK as a special infrastructure program. So that helps us a lot, because it gets us direct access to all the other departments who could cause bottlenecks in delivery. So I think you're all familiar with the Square Kilometre Array. Ultimately, it will look like this. There will be the mid-frequency arrays in Africa, so the dish array, which will be about 3,000 dishes. They won't look like that, they'll have feeds at the bottom. And then the aperture arrays, which are essentially fisheye lenses. And then in Western Australia, you'll have the low-frequency array. And of course, this will be the biggest telescope ever built, and will probably dominate mid-frequency radio astronomy and low-frequency radio astronomy for a very long time. The SKA organization currently has 11 members. As you probably know, Germany has given notice that they're going to leave in July, but I suspect that within a year or two they'll be back. And Spain and Portugal are in the process of joining. France has indicated that it's interested, so has Japan, and South Korea and the USA attend the board meeting as observers. So it's a really global project, which it has to be to afford the money required. At the moment, we're building the precursor telescopes, the Meerkat in South Africa and the ASCAP in Western Australia. Both of them are intended to start doing science from 2016, and they will be integrated into the first phase of the SKA about 2021. So we have a long period in South Africa, where we'll be operating the Meerkat, doing our large survey program and PI programs as well. Then SK Phase 1 is currently in the pre-construction phase, where a number of international teams are doing the design of the telescope and of the systems, and that is intended to be completed in 2016, and the designs will go out on tender in 2017, so the first phase of construction will start in 2018, and scheduled to be completed about 2022. The early science of part of the SK Phase 1 should start about 2020. So the nice thing about an array, as you know, is you can start doing science before you've completed the array. Then the design of the SK Part 2 will start about 2018. SK 1 is approximately 10% of the total SK, so it will be a very significant telescope on its own, and will do transformational science in the first phase. The second phase, of course, will blow that out of the water. So construction of the second phase is scheduled to start about 2023, and the 2030 date I put there is a thumbs up. There's no date fixed at the present time, but I think that's probably realistic. So the current status, the pre-construction work packages designing the various systems are due to do what are called preliminary design reviews, December, January and February. Then we're doing a process called rebaselining. Rebaselining is a euphemism for de-scoping, because you have to fit SK1 into 650 million euros, which is the cost cap for the construction set by the board. And currently the estimated cost is quite a lot more than that, so there's going to have to be some cutting, but we believe that we can do it without impacting the science in any major way. The board of the SK organisation consists of representatives of all the member countries, and it's being advised by the Science and Engineering Advisory Committee and the Science Review Panel. Roy sits on that Science Review Panel. And they're busy with prioritising the science to be input into the rebaselining process. There are also negotiations ongoing for a treaty organisation to be established, and we're negotiating how much each country will pay and how the procurement will work, because many countries want to give their contributions in kind, not in cash. So we've established a site for the SKA in a place where there's very little radio frequency interference. As you know, the problem with a radio telescope in an urban area is the same as the problem with an optical telescope in an urban area. You can't see the universe. So if you were to try to see the sky, see the universe in a big urban area, you would just see the big sky. Same with the radio telescope, where you've got a lot of mobile phones and Bluetooth and cars and TV. You only see those things, you don't see the universe. So this is a map of population density in South Africa. That's Johannesburg, that's Cape Town, that's Durban. This is where the people are, and this is where the people aren't. This area is the Northern Cape Province, and you can see it's almost as if somebody built a fence around there to keep people out. So most of this is an arid area called the Karoo, and the SKA will be built there, and then will extend out through Africa and into our neighbouring countries, Namibia, Botswana, Mozambique, and further north. So we have demarcated part of that as a protected area, and Parliament passed a law a couple of years ago which empowered the Minister for Science and Technology to regulate all activities which could interfere with astronomy. And this is a very powerful law. It overcomes any other law which would interfere with it, like mining laws or telecommunication laws. So the Minister of Science and Technology can say, even though you've got a mining license, you can't mine here because it would interfere with SKA. So that's what the site looked like in 2003, when we were still planning it. You can see it's pretty arid. There are a few sheep there, but not very many of those either, and not much else. And this is a map of the area. The nearest town is Carnarvon, which has about 2,000 people living there, and there are about 6,000 people in this entire area. And we had to build the road through the site, which is about 80 kilometers away. And these little towns are very small. So this entire area is regulated. It's about 500 kilometers across. And the Minister of Science and Technology can prohibit any activities there which would interfere. So when the SK is built by 2030, it will extend throughout Africa. You can see up to Kenya and Ghana, Madagascar, Zambia. And we have every 6 months a meeting with the heads of department in those countries, the heads of the science and technology departments, to ensure that Africa is ready for this. So, in the first phase of the SK, we'll be building what's called SK1 mid. In other words, a mid-frequency array, and that will be in the Karoo on our site. So it will consist of our 64 meerkat dishes that we're building and 190 more dishes. And they'll be spread out over about 100 kilometers maximum baseline. And then, of course, SK2, when it's built, will be about 3,000 dishes spread over 3,000 kilometers, giving you a much better resolution. So when SK2 is built, that's what the Karoo will look like, which is a lot more crowded than it is at the moment. The low-frequency array will be in Western Australia. In the first phase, another 60 dishes will be added to the 36 being built by Australia as their precursor. And then, of course, there'll be the mid-frequency aperture arrays. We'll do prototypes in the first phase, but it'll only be built in the second phase. So to establish our site, we had to put in a lot of infrastructure, power lines, 80 kilometers from Fanaroff, the road. We put on big optical fiber on the power lines, and of course the whole site is articulated with optical fiber and power. And a lot of work was done on this power line because you don't want to have sparking on the power line or corona, because that generates radio interference which would interfere with the telescope. So we've now put in the roads and the foundations for the meerkat telescopes. These are very big foundations, very deep and very heavy, to ensure that you have very accurate pointing of the dishes. And you can see there's a hill here. Behind that hill is the telescope, so that adds shielding to what we have here. This is where we assemble the dishes. That's where we assemble the pedestals for the dishes. That's an accommodation block. And over here is what we call the Karoo Array Processor Building, which is a buried building where we put our uninterruptible power supplies, which I'll show you, and all the racks of the processors, because of course all digital electronics causes interference, and you don't want that to interfere with the telescope, because otherwise you've regulated everybody else's interference, but you generate it yourself. So this is a correlator and power building. It's actually underground, and in there we've got 2.5 megawatts of rotary uninterruptible power supplies if the power goes down. And this is a specially shielded room for the computer racks, and we built it big enough that it not only will house the meerkat racks, but also SK Phase 1 racks. And we have a landing strip, so we fly in people, engineers and scientists once a week from Cape Town and Joburg. That's the first meerkat dish, and all the ministers of our African partner countries attended the inauguration earlier this year. You can see it's an offset Gregorian optics. So we have 64 of those dishes, 13.5 meters diameter, an 8-kilometer maximum baseline. That'll be the L-band, so from 0.9 to 1670, so it covers the hydrogen line. And then we'll have UHF band, so it covers hydrogen in the higher redshift areas. And the reason we chose an offset Gregorian as opposed to our prototype, which was prime focus feed, is because you have a much cleaner beam, much lower side lobes, so you're much less likely to get satellite interference and other interference. And of course, just having a cleaner beam allows you to calibrate the fields much better. So in future, we're looking at a high frequency band. And we've also recently been informed that one of our international partners is going to invest a very large amount of money, and I'm talking lots of money, to build S-band receivers for us, mainly for pulsar timing. That will be very welcome. So we're building our telescope according to strict system engineering processes to make sure that we understand what it has to do and then how you have to design it to do that. And we do strict testing all along the line. And we're building prototypes first because we hadn't built a telescope in the past. So we started off with this plastic telescope, which is made of fiberglass. And that's at the Hartbeespoort Observatory near Victoria. And then we built a 7-dish array here, also made of fiberglass, on our site in the Karoo. Those 7 dishes were an engineering prototype, but because they worked so well, they're now in demand for science. A lot of science is being done with them, performing very well, and we're going to be doing VLBI observations with the European VLBI network. So that's available for science now. Sorry, I seem to run ahead. Okay. We've already allocated the first 5 years of the Meerkat's life to large surveys. So the highest priority are doing deep H1 fields, looking at large-scale structure, and then radio pulsar timing. We'll also be mapping nearby galaxies, doing a high redshift absorption line survey, molecules, fast transients, and then some nearby stuff, and then deep surveys in the continuum, which Kurt is involved with. But we're also going to do VLBI and cosmic magnetism. So the time has been allocated to a very wide range of international scientists. You can see more than 300 scientists involved in those teams. The time allocated is more than 5 years, but you can see these are long surveys and we've given plenty of time for them to be completed adequately. What is nice though is that it turns out that we won't need the whole 5 years, because we originally spec'd the Meerkat to have that sensitivity. I wouldn't worry about the units. And then when we did the detailed design, we realized we could get that sensitivity in 2 bands, not just in the 1 band, 900 megahertz to 1.67 gigahertz. But we also added the UHF band, all for the same money, I might add. And so we've got a 41% improvement in sensitivity, which means that we can double the survey speed. So what we were going to take 5 years on, we can do in much less time. And we also have the good frequency coverage now. So we're building a much better instrument for the same amount of money. And that has to be good news. So this is how we put together the backing frame for the Meerkat dishes. We put them on a big truck transport and carry them out to the site. They're lifted up by a crane and put on a pedestal. The receivers that I mentioned, which are giving us very good performance, we also have very good optical design, and they're being done by a local company here in Stellenbosch called EMSS. low risk, well-matured technology. So it's developed local industry, and the nice thing is we've given one of the receivers to the observatory in Penticton in Canada. They've been testing it for us, and they've confirmed that it has outstandingly good characteristics. So for those of you who like these things, and I know you're mainly theorists, this was done in Canada. Let me emphasize, this radio interference is Canadian, not South African. You wouldn't see this on our site. But what you find is that the receiver temperature is between 5 and 6 degrees Kelvin. And we originally measured it at 7, and the design goal was 7.5 Kelvin, so this is very good performance. And we're in fact expecting performance even better than the 310 meters squared per Kelvin that we expected. So more than double the survey speed. We expect something even better than that. Most of the technology has been developed locally. It's a team in our office here in Pinelands, and we've been working on these very flexible computer boards, which we're now selling around the world, and we're commercializing them. But a lot of observatories are using this technology now based on FPGAs. So the work packages that are being carried out around the world for the SKA cover all of the subsystems you can see there. The assembly, integration and verification, that's a system engineering process. We lead that one. Central signal processor led from Canada, but we participate actively in that. The dish is led from Australia, but we're key players in that. The infrastructure package we lead. Then there's low frequency aperture array, mid frequency aperture array, does a longer term signal and data transport, science data processing, because you're planning for exaflop speeds. Telescope manager is the command and control, and then single pixel feeds, which are being developed mainly in Sweden. On our site, we also have the paper telescope looking at the EOR. This is a joint project with the National Radio Astronomy Observatory, Berkeley, Virginia, and Pennsylvania. And there are 128 antennas on the site, and they're doing a year's worth of observations now, hoping to get the first signals from the EOR. But they've also made application to National Science Foundation, and they have the first $2.5 million to put in a prototype array, so we'll be starting to build that on our site quite soon, putting in 38 antennas, and then hopefully extending it where they get more money from the NSF. And University of KwaZulu-Natal is looking at another H1 array, which we'll probably put on our site. We also have the CBAS project that we're doing with Caltech and Manchester and JPL and Saudi Arabia. We have 2 antennas for that in South Africa, one at Hartbeespoort and one in Peru, and there's one in Owens Valley in California, and that's to look at foregrounds, polarized foregrounds, so that you can get a very clean observation of polarized cosmic microwave background observations. Now we'll only be building in our African partner countries after 2022. So in order to build up institutional capacity and technical and scientific capacity, we've started a project which we call the African VLBI Network. The idea is to take slightly used second-hand dishes in various countries which are operated as satellite communication dishes and convert them for radio astronomy. So Vodafone, the international mobile operator, has given that to the Ghanaian government, and we're working with them to convert it. You can see there. And then this is in Kenya, a place called Lomanot, where Orange Telecom is going to give that dish to the Kenyan government, and we'll convert that. And we're using it as an opportunity to train people. So these are young engineers and scientists from Ghana who spent 6 months here in Cape Town for training on the technology of the dish. We also have a big, what we call human capital program, where we've given out a lot of bursaries over the years from 2005. Every year in December we run a conference for our graduate bursary holders. So that was in 2012. I don't have the more up-to-date pictures, unfortunately. But you can see it's quite a big group. We've given bursaries to students from many other countries, and many of them have gone back to their home countries and started teaching astronomy. So in Nairobi in Kenya is the first astrophysics program now. And we also do workshops together with the African Institute for Mathematical Sciences, AIMS, in various countries, where we introduce people to computational issues applied to astrophysics. And that was in Nairobi, but we've done in Namibia as well, and in Mauritius, and we're planning a number of others. We've also launched a big data program. The obvious commercial spin-off from the SKA is in big data, because the SKA, of course, will produce about 100 times as much data as the entire internet. So we're talking about lots of data at high speed. So it's a way of training up people in big data. The UK government has invested £100 million in the SKA, and they say it's mainly to develop big data capacity in the UK. When we were in China for the board meeting last month, the provincial governor told us they're investing 2 billion rand in high-performance computers around the SKA, because they also want to become players in big data. So everybody's getting on that bandwagon, and we are too working with UCT and UWC and others to develop centers of excellence in big data, working with IBM and Cisco and Intel and others as partners. So that's our human capital bursary program. As you can see, we've given 612 grants in all. We give them across the spectrum, from research chairs and supporting the universities there, but we also do postdocs, PhDs, MScs. We support the NASP honours courses, BTech, Bachelor of Technology, that's undergraduate physics and engineering. We do national diplomas and further education training to develop artisans. So we're doing it right across the spectrum, from artisan and technician training to research chairs. And the Department of Science and Technology is investing heavily in this. We've been trying to get more women into the program. We're doing fairly well, but not as well as we want to do. And what we've been trying to do is to create a pipeline where we take students from school and take them right through to a postdoc. And that's starting to work now. In particular, we've wanted to do this for black students, because we found when we had postgraduate bursaries, we weren't getting many black students into those bursaries. So we're now taking people, as I say, from school, from first and second year undergraduate, and putting them all the way through, and it's starting to produce good results now. We also have what we call a Young Professionals program, where we're taking our best students and bring them into full-time positions in the SK office. Thanks.
Time for a few questions. Yeah. Yes.
Yes, one question. What red shift frequency range are you going to use for KAT1? I mean, your first phase of the COT, and then your one that goes up to 2030. What are the regimes of the red shift that or what you're going to give birth?
So with the meerkat, we'll be observing the lowest frequency will be about 600 megs. So observing out a redshift of just over 1. And then with SK1, there's still debate on what the frequency bands will be, but the intention is to go out as close to redshift of 2 as possible. And SK2 is going to be designed from 2018 onwards, but the intention is to go right back to the EOR.
Thank you. Thank you.
Any other question? Question there? Yeah.
Thank you enough to perhaps emphasize the key capacity development, but when I look across the audience, I'm wondering how many of all these people we've talked about, where are they?
They haven't got up yet.
Then we need staff to help them.
We do need staff to help them. We need as many supervisors as we can get.
Any other questions?
And we're looking forward to universities to invest in that. In case Dr. Price is listening.
Yes.
Yeah, you mentioned in one of your slides that you had the Newton Fund there. This is a collaboration with the UK, right?
Yep.
So how do you, they usually require that you justify that this has direct impact, research, the economy of the given country and so on, don't they? They usually need to have direct technical applications and economical in the kind of project?
Not in this Newton Fund.
Not in this one.
No, so it's being advertised now. There will be £4 million over 5 years for collaborative programs between UK institutions and South African institutions. But there's no requirement of direct applicability.
Okay, some other countries they will.
Yeah.
Okay, one last question. If not, let's thank Fergie, Fanaroff again. Our next speaker is David Bacon. And he will speak about observational windows on gravity. Thanks, David.
Thank you. So it's a pleasure to carry on from the previous talk, which was saying how important SKA will be. And one of the things that SKA will be crucial in is understanding gravity at a very precise level. And we'll get to that in a little while. As you know, observational cosmology is reaching a stage where it is data rich. There's a large amount of data coming and many important surveys being designed. So now we're at a stage where we can start to look at gravity in detail on cosmic scales. This requires the work of an awful lot of people. What I'm presenting today is not just my work, but has very important contributions from the people on the screen there. So, at the start of the conference, we can be optimistic. The cosmology is in a very good state, apparently. We've got this picture of the universe that seems to hold up to some degree. So the general idea is that we would have a Big Bang with an inflationary period. Things evolve until we get to the stage of the cosmic microwave background. Then as time goes on, we have dark matter clumping into clusters and filaments, the normal baryonic matter falling into those gravitational potential wells, galaxies forming, and here we are. So that sounds really great, and indeed it is extremely successful, our current model. If we look at the Planck results, for instance, we find that the power spectrum of the temperature fluctuations in the cosmic microwave background is extremely well fit. The dots are the data, the green lines are a fairly simple cosmological model with only a handful of parameters, And the components that go into it are our ordinary matter, a large amount of dark matter, some invisible material that interacts gravitationally, and an even larger amount of dark energy that accounts for the fact that at the present time, the universe is not just expanding, but expanding at an ever-increasing rate. It's accelerating. So this is very exciting, but it is both interesting and overly provocative, perhaps, to say something like this. Is all well with cosmology if we postulate two ethers? So the idea of the ether over a century ago was that there's some sort of medium that is the medium that electromagnetic radiation propagates through, and in that context things seem to be working nicely, but of course it turned out that postulate was very wrong and was shown to be wrong observationally, and then we had Einstein's theory, which was quite different, which accounted for it in a different way. It's an interesting question for me to ask, because surely we want to be open to that, we want to be open to a revolution, but it's also perhaps overly provocative, because I would say that, take for instance the CMB spectrum there, that's an incredible success. That doesn't happen by accident, I would have thought, by postulating these two quantities, dark matter and dark energy. So these two ethers, as it were, have already passed very, very stringent tests. But maybe we're wrong. And another way of thinking about it might be, let's suppose that these quantities, at least one of them, if not two of them, were due to some misunderstanding of gravity instead. So that's a topic for you to argue over at coffee. If we look at gravity in the universe then, it's a very nice way of dramatising what we might want to be testing, given by Celsius. Here is the gravitational potential in the universe at different scales, and here is the curvature of the metric at different scales. We can see that the typical length scales in the universe fall on the blue lines, and the typical mass scales in the universe fall on the red lines. Almost all of the precision gravity tests that we've done so far lie towards the top of that diagram. If you look at one Earth radius or one stellar radius, that's where we've got solar system tests and also the Hulse-Taylor pulsar tests. So we really believe that general relativity is doing well there. I think there's probably a point of it. There we go. What cosmology has to contribute is this region here. Many decades away from where the tests have been made. Who promised us that the laws of gravity which we've tested over here don't roll over when we go way down here? And that's what we need to test very precisely. So how can we test it? There's various different probes that we can have on cosmic scales of gravity. And one very important one is gravitational lensing. For those of you who are from a particle physics background, you might be pleased to consider this a very large scattering experiment. What we've got is, in the background here, we've got very distant galaxies, let's suppose 8 billion light years away, something like that. These galaxies have got shapes, and let's say, for simplicity, that those shapes are randomly orientated with respect to each other. Then the light from these galaxies comes through the scattering material, which in this case is a combination of dark matter and normal matter. The scattering is gravitational scattering. So the light bends as it goes through because of Einstein's theory of general relativity. And so when we see these objects, which were randomly orientated here, because they've come through similar bendings along this line of sight, they turn out to be correlated in shape when we see them in our actual observed sky. So if we can measure the correlations between shapes on different scales, then we're learning something about the gravity. So it's a scattering experiment of that sort. It turns out to be, at least at an introductory level, a very nice, simple probe. I'm going to skate over many, many issues, you understand, but at least the concept is nice and easy. The idea is that the position, the coordinates at which you see a source, which are these coordinates in the image plane, are related to the coordinates on the sky if there was no lensing, simply by a 2 by 2 matrix. And this 2 by 2 matrix is very simple. It's got an isotropic part and an anisotropic part, so that if you started with a galaxy of radius 1 in an unlensed universe, then what happens is it gets maybe a bit bigger or smaller. That's called the convergence effect. And it can also be distorted into an ellipse. That's the shear effect. And why it's attractive as a gravitational probe is that those quantities, this expansion of an object or shearing of an object, are very simply related to the gravitational potential. So if you squash the gravitational potential along your line of sight with some geometric factors and the time part and space part of the potential that you'd see in the metric, and if you introduce a gradient on the sky, then look how simple this expansion is. This dilation is just related to a second derivative of the projected gravitational potential. And same here, the shear is related to a different set of second derivatives of the gravitational potential. So that's why it's attractive. There's many reasons why it's a bit of a honey trap. People get attracted to it and then realise that there's many, many problematic systematics to this probe. But still, it's a very exciting idea. And if we can measure, for instance, the ellipticities of objects, which estimate this shear, then we can estimate a projected gravitational potential, or we can even invert to get to kappa, which is also a way of talking about the projected density. So this is now being done. This is, for instance, with very early results from the Dark Energy Survey, which are now on AstroPH. This is work led by Peter Melchior and involving many of us in the weak lensing group of the Dark Energy Survey. Here are some of the images of clusters, typically at redshift 0.2 to 0.4, that Des is now observing. And these blue-green scale contours are the density maps. If you like, it's a gravity map which has been measured by taking every single little galaxy here, measuring its ellipticity, and then converting by the equations on the previous slide to look at what would have caused it in terms of the density. So this is very exciting. We can now start to look at the relationship between these contours that are telling you about the gravity and the black points which are telling you about the cluster members for these clusters. And this sort of approach is sensitive to dark and baryonic matter. It's sensitive to Poisson's equation. We've assumed the normal relationship between density and potential. Of course, that might be at jeopardy if we want to test gravity. And it also is important that we're assuming a particular relationship between the time and space potentials, the relationship that general relativity gives us. But again, that might be wrong. Not only can you make maps, but you can also look at this lensing in a statistical way. So what you can do is you can take the ellipticity of one object separated on the sky by angle theta from another object, and you can look at the product of their ellipticities, so the correlation function of their shears, as you get to increasing separations theta. So this is work done by Fergus Simpson and collaborators with the CFHT lens survey, and this is the amount of correlation you get as you increase theta. So if objects are nearby to each other, yes, they are very well correlated. That's like the cartoon I showed you of the scattering experiment. And if you go to larger theta, then they become less correlated. General relativity can predict what you'd expect in the standard cosmological model, and it fits reasonably with these different data, although not straight through the data. And you can then start to play with gravity, so you can change how Poisson's equation works. Maybe Poisson works, but the gravity is 10% stronger than Poisson would predict. Or you can start to look at the relationship between the different time and space path potentials and how that would affect your lensing. So this is the beginning of testing gravity with this probe. Now we're at a stage where I can introduce to you the cartoon of how we're going to test gravity on these large scales of the universe. So how do we do it? If we think this is the Newtonian gauge of the perturbed Friedmann-Robertson-Walker metric, so this is like a typical homogeneous, isotropic, expanding universe, but you're allowing little perturbations which are, if you like, the gravitational potential in the time part and the space part of the metric. Now, how do different cosmological quantities relate to this metric? Well, first of all, the lensing notices both the time part and the space part of this metric as the ray travels through the universe. So this lensing feels the time part and the space part potential in this metric. So here's a mass, it's causing a gravitational potential. Indeed, this lensing feels both psi and phi. Poisson's equation involves relating this mass to the potential psi. And non-relativistic objects, like let's say another galaxy, will feel this gravitational potential psi only, not phi as well. Because this galaxy, let's say, is moving non-relativistically. And so this object will behave as though it's feeling psi. So if there's any difference between psi and phi, this way of doing things, if we measure both the lensing and the dynamics of non-relativistic frames, that will help us to see what's going on with gravity. So we've got this three-way test. We've got this fact that mass causes psi via Poisson, which might be a Kennedy. Then we've got non-relativistic objects moving by psi. And then if there's any difference also between psi and phi, the ratio of psi and phi are not 1, then lensing will tell us about that as well. So, we've talked about the lensing, but you can see that this is not going to tell us everything. We've got this degeneracy between psi and phi here, so we need this non-relativistic probe as well. And one of the ways to do that is to look at velocities in the universe of galaxies, which are often moving at non-relativistic speeds. So the way that people often do this is with so-called redshift space distortions. This is what's going on. Suppose you've got, like on the previous slide, a gravitational potential here at psi, and these galaxies, which are at equal distances from the centre, respond to that psi. They start moving according to the gradient of the psi field. So they've got velocities, which we can see by the arrows. Imagine that I've got my eye at the bottom of the screen looking up at this. Then this object, because it's moving away, will have a slightly larger redshift than usual for that distance away from us. This object will be slightly blue shifted. So these objects, although they're moving, there's nothing I can see about the fact that they're moving on a spectrum or an image. So what I would infer in a redshift space way of plotting these in 3D is that these objects were where they really are, but this object's been moved up a bit and this object's been moved down a bit. So an isotropic situation like this actually turns out to be anisotropic, squelched, because of these velocities, which are in turn due to this gravitational potential. If the objects are quite close to each other in a dense region, let's say a cluster, then this object might be moving in this direction, this object might be moving in this direction, and so on. So that now what happens is that this object has been given such a kick in redshift that it ends up over here. This object is given such a kick in blue shift that it ends up over here. So you get this cigar shape of objects, which we call the fingers of God. And if you look at the correlations of galaxies, this is transversely on the sky, and this is radially away from us, then you do indeed get these patterns. On large scales, you get this slight squelching of the correlation function due to this effect, and on small scales, you get this strong cigar shape because objects have actually crossed paths to make this strong ellipse. So we can measure this and hence understand about the statistics of psi in the universe. So we've done this. One of the tests that we've done is to take CFHT lens data and Sloan DR7 velocity data and to look at what they tell us about gravity. So you can look at varying this mu, which is the modification to the Poisson, this Poisson a bit stronger than you might expect. And you can also vary a quantity called sigma, which is the modification to the lensing density relation. You can fit your data with those predictions with different parameters here, and you find that the CFHT lens data at the minute allows this pink region, and the velocity data allows this green region. Therefore, if you combine these two, then yes, indeed, you're breaking the degeneracies to learn about both the psi plus phi and the mu, the Poisson parts of the problem. There are different ways of measuring velocities, and one which has been something that quite a few people in this room have been interested in the last year or two, is something called Doppler lensing or Doppler magnification. So this is a new way of trying to look at these velocities. The idea here is something that, because we've now looked at velocities, hopefully you'll be able to get your head around. Here's the observer, and here's a galaxy that's in the middle of the gravitational potential. Here's a galaxy that's moving towards the middle, and here's a galaxy further away moving towards the middle. Now let's think about the sizes of those objects. Let's suppose that they all have the same physical size. C, D, and B all have size 1 in some units. That's the physical size, but C is nearer to us, so on angular size on the sky, it looks bigger. D looks normal, and B looks smaller, because it's further away. The cosmological part of the redshift for C, let's say it's, for instance, 0.1. This is all very, this is not actual numbers, this is an exaggeration so that we can understand. Let's suppose that C is at redshift 0.1, D is at redshift 0.15, and B is at redshift 0.2. But, as we've said for redshift-based distortions, C is given a kick in redshift because it's moving away from us. B is given a kick down in redshift because it's moving towards us. So the total redshift will be bigger than usual for object C, the usual for object D, and less than usual for object B. So in this exaggerated case, they all end up at the same observed redshift, even though they're actually at different distances away from us. And then we measure the angular size, we measure the actual redshift, the observed redshift, and we infer how big, how far away these objects are, because we say, oh, right, all objects are about this radius. So how far away is it? We infer that this one is at 450 megaparsecs away, because it's got this particular observed redshift. We infer that that one's 450 megaparsecs away, because it's got the same redshift, and we infer that one. So we think they're all the same distance away, but this one looks big for that distance, and that one looks small for that same distance. So you can see that there's a crosstalk between the velocities of objects, which give you an observed redshift which is different from their cosmological redshift, and the size that we think those objects are. So if things are moving away from us, then we infer that they are bigger than usual, and if things are moving towards us, we infer that they are smaller than usual. This is the Doppler magnification effect, and it works in the opposite sense to gravitational lensing. So this was first pointed out by Camille Bonvat, who will be speaking a bit later, and she worked out that this extra size to an object is related to the velocity and some geometrical factors. This year, a group of us have been looking at this in simulations and working out cosmological predictions for it. Here is, in the Millennium simulation, as a function of redshift away, how much of a particular line of sight we get this Doppler lensing extra size. And you can see that as you cut through large-scale structure, you get lots and lots of fluctuations in the size of objects. If you zoom in around a void here, you see that in front of the void, you've got smaller sizes than usual, and behind the void, you've got larger sizes than usual. And this can be several % effect, so it's something that can be measured on the sizes of objects. One of the nice things you can do with this is that you can take any estimates of excess size of objects, and if you integrate along the redshift direction with a window function, W, then it's closely related to the gravitational potential along that line of sight. So what you can do, this is in a simulation, the Millennium simulation, you can do this and you can get a prediction of what the gravitational potential is in 3D in the whole patch of universe. And this is the reconstruction that you get with realistic observations of sizes, including realistic size noise in that region. So you can recover the gravitational potential in the universe via estimating these sizes and then integrating along the line of sight. So we're now doing this with the Sloan Digital Sky Survey. Here is the Sloan Telescope in New Mexico. This is the whole sky, so this is RA and declination. This is we're looking at a 4,000 square degree region in this part of the coverage of Sloan. And what Sloan have done is they have, with great care, they've measured the sizes and magnitudes by fitting to each object different galaxy models. Then I've matched the photometric quantities like this with the spectroscopic redshifts for a large sample of objects. And for instance, at each redshift slice, here a redshift slice around redshift 0.1, we get a large set of galaxies that we can estimate this Doppler magnification for. It's excess size. So here's the provisional map when I do the estimates and integrate along the line of sight. This is the X and Y directions on the sky, and this is the redshift direction away from us. And these are isocontours of the gravitational potential, similar to what was seen in the simulations there. This is provisional work. I'm now comparing this Doppler potential map with the potential inferred from the galaxy over density. It's looking good, but I'm not going to tell you the result today. Another thing that we're looking at is the statistical measurements of this Doppler magnification to measure the velocities. So what you can do is you can take the number density of objects and correlate with the excess size of objects due to this Doppler effect. So here is a particular galaxy that we're counting, and here's a particular galaxy that we're measuring the size of. It's a distance zeta behind and a distance x across the sky. What would we expect if we did this correlation? We'd expect, just like the introductory cartoon I showed you, that if there is an overdensity here, we expect kappa to be negative behind it. We expect a slight decrease in size behind this overdensity. We'd expect if the red galaxy was here in front of the black galaxy, we'd expect kappa to be positive. We'd expect it to look a bit bigger than usual. We'd also expect that as we go around this sphere, that because a galaxy here, this galaxy would be moving transverse to the line of sight, we wouldn't expect any observed transverse radial velocity, so we wouldn't see anything. Therefore, kappa will be fading off as cos theta grows. We'd expect something like the fingers of God if we have small x and zeta, where an object here, which should be too big, is actually pushed the other side of the object. So we'd expect some sort of flipping to go on at small x and zeta. And also there's an annoying feature, as there always is with these probes. It might be that there really is an intrinsic size correlation of these objects with an overdensity. This is nothing to do with Doppler lensing, it's just that galaxies might be bigger or smaller near an overdensity. But we'd expect that to be symmetric on this sphere. We don't expect objects to be preferentially correlated but small on this side and correlated but big on this side. So any intrinsic correlations in size should be symmetric. So again, you can do this with Sloan and measure. This is the x direction and this is the zeta direction behind and in front of the overdensity. This is the symmetric part. Indeed, you do see a correlation of sizes at small scales. This would be the intrinsic correlations. And then the antisymmetric part should contain the Doppler magnification. And indeed, you see that the size is lower in the background and larger in the foreground. And it fades off with cos theta. And also, you can see that it flips at small scales, which is the fingers of God issue. These are the noise contours. This is very exciting. The next step then is to use this approach to velocities to constrain cosmological parameters and bias. And then with the spirit of the psi and phi plus psi cartoon, we can look at what the Doppler magnification signal gives us and compare with what the lensing signal gives us to test the gravity. This is very promising, but there are other ways which we can do right now of combining lensing and non-relativistic probes to look at gravity. And I'm now going to go on to that. So recently we've been doing some work with clusters to, again, compare lensing and non-relativistic probes. The context in which we've done that is a particular feature of gravity on large scales, which we expect, called the chameleon mechanism. The idea here is that there's quite a large class of modifications to general relativity where when you make the modification you get an extra degree of freedom. A scalar degree of freedom that will give you a fifth force. So objects will not just feel the normal gravitational force but something extra as well from this scalar potential. That is clearly not true on solar system scales because we've got all of these great tests of general relativity. There's no extra force where we are. And the only way that you can have both of those things to be true, well, no, sorry, that's too strong. One way in which you can have both of those things to be true is if you've got a chameleon mechanism where the fifth force is screened when you get to high densities like the solar system. What this means in detail is that the scalar field is such that in high density regimes, the mass of the scalar becomes very large and it stops acting as a fifth force. The constraints on this sort of approach are very good on solar system scales. They're also reasonable on very large scales. I'm now going to talk about the work that we did to get this constraint on intermediate scales, cluster scales, which is currently, I think, the best constraint on cosmological scales of the efficiency of the streaming. So here's again the cartoon to show you what's happening. We have a cluster galaxies. In the central region, where the density is sufficiently large, then the chameleon mechanism will say that we are screened and there is no fifth force. Further out, where the density is not so great, then we would get a fifth force. So the X-ray emitting gas, which is basically non-relativistic in clusters, will feel the fifth force on the outskirts of clusters, about a megaparsec away from the centre. Whereas the lensing doesn't feel the fifth force, it just goes according to the metric as usual. So what you can do is you can fit the X-ray emitting gas profile and the lensing data, the shears around these clusters. You can fit it for particular chameleon parameters, the strength of this chameleon force, this scalar, this fifth force, and the effectiveness of the screening. So this is what we did. This is work led by a PhD student in Hiroshima with contributions from us in Portsmouth. What we did is with a single cluster, that's the coma cluster, we took the Subaru weak lensing data, the XMM Newton X-ray data, the Planck Sunyaev-Zeldovich data, and we looked at what that would imply about the mass within a distance R of the centre of the cluster. The light blue shaded is the re-lensing permitted region, and then the blue is if you've got the X-rays, and the black is if you use the SZ. And then you fit that data with chameleon parameters, beta, fifth force strength, and phi infinity, the screening efficiency. And we get this constraint if beta was really weak, if the force is really weak, then you can't constrain it. If the screening is very, very weak, if the screening is such that you would be within the GR context, then you can't constrain it. But this is the region where you would see a chameleon force with this data, and we don't. And this, therefore, is a very strong constraint upon the screening efficiency of a chameleon mechanism. We're now doing this with a much larger set of objects at a much greater redshift. So we want to do this at cosmological redshifts. This is with XMM clusters that are found in the CFHT lens survey. So we get the lensing data from there. Now the median redshift is 0.7 or 0.8. We're using this X-ray data from the XMM LSS survey, and now we have 52 clusters which are matched between them. We take several different X-ray temperature bins, that's like taking different mass bins that we can now do. And then with the stacked profiles, which are made on X-ray centroids, for both the X-ray surface brightness and the lensing, then we can look what we get. So here's an example of the stack. We get this beautiful X-ray surface brightness profile as a function of distance that we can fit with an NFW profile plus X-ray gas model. And you've got this shear data. Again, if the shear is nearby to the cluster, it's strong. If it's further away from the cluster, it's weak. And again, you can fit this very nicely with the same model. The blue is general relativity. The red is our best fit with chameleon parameters added. You can see that there's no evidence for chameleon, which is a constraint on chameleon. If the chameleon was doing this, that clearly doesn't fit. And therefore, that particular set of chameleon parameters is excluded. And again, here we are, this is the strength of the fifth force. This is the screening efficiency of the chameleon. And again, we get an excluded region, which gives us, in the language of F(r) models, a good constraint on cosmological scales now of what F(r) should be. Again, this is a screening efficiency. This is competitive with the best constraints on cosmological scales. Now we'll do this not just with the CFHT lens survey, but with the dark energy survey, which will give us 4 times as many clusters with X-rays already, before we even think about the future when the many thousands of clusters with DES could be hopefully observed with X-rays in the future. So to finish then, just this claim about the future of this area of testing gravity with observations. So here we have the square kilometre array, and this is the LSST, the Large Synoptic Survey Telescope. It won't actually be amongst the SKA antennae, it will actually be the other side of the world in Chile. But the important thing is that SKA can measure these lensing shapes. It can also measure the velocities through the both the Doppler magnification and the redshift space distortions. LSST will also be excellent at measuring clustering and gravitational lensing. So combining these two gives us again this way of looking at both the relativistic and non-relativistic behaviours. These are some predictions. You get such strong constraints from these two telescopes that you don't just have to break down your gravity test into just a single number. How much stronger than Poisson is it? How much stronger than usual lensing is it? Instead, you can break it into functions of redshift and scale. So how much is Poisson different on different scales and different redshifts? So you break down your function, this is a Poisson modification for instance, into a sum of basis functions which themselves are functions of redshift and scale. So you can say how much of a particular function is there of this breakdown of tests of gravity. So I've written like that. Allow gravity parameters to be scale and z-dependent functions. You can do a PCA analysis to find out what are the best functions to choose, which are the most different from each other and the most constrained by these experiments. And here we have the error upon this Poisson function, and this is counting all of the different functions that we can constrain. So you can see that with, for instance, SKA1 alone, this is the pink points, then we can measure maybe 2 different functions of redshift and scale to 1% accuracy to test Poisson. Or we can measure 1, 2, 3, 4, 5, 6 up to 10% accuracy. If we combine Planck, LSST and SKA2, then we can measure about 10 different functions of redshift and scale to 1% accuracy as a breakdown of the Poisson equation. Similarly, if you look at the potential, the time part of the potential and the space part of the potential, the ratio between those two, again, once you've got to LSST and SKA2, then we have 10 different functions to 10% accuracy. So at that stage, we're really understanding what gravity does on many different scales and evolving with time. So here are my conclusions then. Gravity on cosmological scales, I hope I've convinced you, is a very interesting thing to look at. It may well be that lambda CDM is right, but what if it's not? Doppler magnification and lensing allow you to do both gravity maps and statistics on large scales with different potentials. So you can start to look at the relationship between those two. You can also look at clusters, which give you both the lensing and the non-relativistic part. And that gives you very stringent tests already of the chameleon mechanism on cosmic scales. And future surveys will allow very excellent constraints on large-scale gravity parameters, moving from a couple of poorly constrained numbers now to many, many well-constrained functions of redshift and scale in the future. Thank you very much.
Questions?
Let me come to the observation of the chameleon mechanism. You need a chameleon mechanism when you have a potentially dangerous fifth force, namely when the ratio between nuclear mass and plant mass depends on the scale of the phi.
Yep.
So now the chameleon mechanism tells you that phi has settled inside the object at a different value from the outside. That's the
Okay.
essence of it. But that means that the strength of gravity is different inside the object and outside. That can be in principle measured.
Yes.
So my question is, how do the type of constraints you get compare with constraints that you would get by just measure for possible density dependence of couplings inside dense objects? I mean, that is many years ago I worked out this piece olive thumb bounds. I don't know, remember what they were, how density will affect this type of mechanism. The gravitational force, and there are definitely bounds. I'm sure the bounds are much better now, but I would be curious, I mean, how well they are, because these are just two sides of the same mechanism.
So are you saying you measure a proxy for density?
Yeah, you know the density of objects,
Yeah.
let's say the density of a cluster or something like that, and then the gravity inside this cluster will be stronger or weaker depending on which side it goes.
Yeah.
And you get bounds on it. I think at the time with piece we worked with supernovae and other objects like that, but it's the same principle. I mean, we called it at the time density-dependent couplings. It was long before it was called chameleon mechanism, but it's the same.
Sure, yeah.
And there should be, you know, of course, dynamical things.
Yeah.
And there should be also directly tests of how strong is gravity in a given dense object.
So I think we should discuss this further at coffee, but I think you're talking about the same thing, right? So lensing is a way of measuring the density,
Sure. Okay.
various effect potential, so it can be mixed up with that. And the X-rays are, the X-ray temperature is also a way of measuring the density, but under the assumptions, under different assumptions. It's non-relativistic material. So combining those two, I think, is doing what you're saying.
Do you think in principle you could phrase your chameleon bounds as bounds on how the gravitational attraction depends on density?
Yes.
Okay, that would be interesting to phrase it in that because it's very easy to visualize in this case.
Yeah, yeah. I'd like to talk more with you because I'm not entirely sure, but I think it's the same thing we're talking about.
Yeah.
I have a short comment and a short question. There are hopes and even some realistic possibility of using VRBI and super VRBI observation to measure proper motions in a very, very distant object that will allow you to go to another window guide them very large.
How far?
Well, in super VRBI observation you can reach Rashid 1 or even larger. And if you use millimeter super VRBI observation you can reach Rashid almost 2 probably 5%. Then the question that I have is, what do you think? Can you comment about that? And the very short question is the following. When you use chameleon tests on cluster galaxies using X-rays, the other parts, you are very sensitive to clamping of X-rays, which introduce a lot of biases in temperature.
Yeah, I agree.
If you use LC only, then you are almost clear this time.
Yes, yeah.
What happens if you use SD only observation to test chameleon?
Yes. So
instead of
so we did that with the Tolkien et al. Paper, and it is consistent. Yes.
Okay.
But of course, that's for a particular cluster, which is Coma. We'll want to do that in future for all sample at large dimensions.
What do you think about the super VRBI?
Oh, it sounds wonderful. Yeah, let's think about that.
Ruth?
I just had a question. You said that in the chameleon mechanism, also the same topic of your talk, you said that lensing is not affected by the chameleon. Doesn't the chameleon couple universally to matter and radiation in the same way?
I don't think that's in our model, but we can check afterwards.
Yeah. So, I mean, if it comes from an FFR, you would expect that.
Well, usually it comes to the trace of the stress analysis, so it's like a 5T coupling.
And then it's matter.
So it doesn't couple to light.
So, I mean, for photons, the traceless part of the stress tensor is not there
Okay.
Usually it's just a scalar field. It will couple to matter by density-dependent masses. That's the essence in a certain sense.
Yeah, but it
And
comes
then light is not coupled.
because it couples with the
Unless it has this derivative coupling.
Yeah.
So my understanding is there's an indirect
Two more
relationship.
complicated things.
Yeah. So there's an indirect issue, which is the chameleon force will change the density of the material, which then in turn changes phi plus pi, which then in turn
Yeah.
affects the lensing. And that's a different matter.
Thank you.
But just Ruth, sorry, it couples to matter through a conformal coupling, so you don't
Yeah,
see light in
yeah,
that way.
yeah.
But it can couple to light through an F square. So in the presence of an electromagnetic field, then you see the coupling to photons.
Okay.
So
Yeah.
they're two actually different couplings that are both allowed.
Thank you.
Okay, thanks very much. Our next speaker is Gianfranco Bertone. Folks on the dark matter searches.
All right, so let me start by thanking the organizers. I think for many of us is the first time in South Africa, so thanks a lot for this opportunity. And I would like also to thank the previous speaker for so nicely introducing the problems of Lambda CDM. The central one being really that we need to convince ourselves that what we're not dealing with is another or two more ethers. So what I want to do today is to discuss a little bit what strategies have been proposed to discover at least the particle evidence of at least one of these ethers, in particular dark matter. So you've seen, basically the status of the field, with the usual, pie chart that we usually show with, dark energy contributing most of the matter energy budget of the universe, and then dark matter, and then baryons. One thing that maybe I can add on top of what has been said already is that that particular statement, of course, is a statement about the status of the universe today. So the relative contribution of dark energy, dark matter, and baryons varies with time, obviously. So in particular, dark energies is completely subdominant at the epoch where structures start to form. What does not depend on time, almost does not depend on time, is the relative abundance between baryons, so ordinary matter, and dark matter. And in standard cosmology, we get a very precise measurement of the relative abundance, the absolute and the relative, therefore, abundance of dark matter and baryons. And we know that 85% of the matter in the universe is dark. Okay, so this presentation is precisely about how do we find the particle evidence, how do we detect the particles if we are dealing with particles of dark matter. And the central question, of course, is how do we detect something we know nothing about? We have a wide range of possibilities to explain dark matter from a theoretical point of view. How do we build experiments to search for these particles? So this is the central question of the talk. How do we detect dark matter particles? And in particular, how do we identify dark matter particles? Suppose that you run an experiment, you find a rate of events, for instance, in direct detection experiments, or new particles at the Large Hadron Collider. How do we make sure that these particles that we've discovered are the dark matter in the universe? And let me start with a couple of introductory remarks. The first one is about the history of dark matter. I just want to spend really 2 minutes about that. I think, so I got a bit interested in this issue with, there's a professor in the history of science at the University of Amsterdam, so we've been discussing, several aspects of the history of dark matter. And, usually we tend in these conferences to summarize the evidence for dark matter with, Zwicky, 1930s, Vera Rubin, 1970s, that's it. But the history of dark matter is, of course, much more complex, and I think we should do better also as a community to acknowledge the efforts of the pioneers who, established the dark matter paradigm throughout the years. And I think it's particularly interesting here, since we heard so much about SKA and radio telescopes, that radio telescopes were actually very important in establishing the dark matter paradigm, even before the 1970s, actually. And there's a beautiful history. There's a lot of interest of people who made important discoveries, in particular about the existence of flat rotation curves in the outer parts of galaxies. It's a very interesting story, and I think we should really give credit to all the pioneers in this field. Let me just mention, for the purpose of this, this review talk, that there are three phases, I would say, in the history of dark matter. One is the discovery of anomalies. So the fact that there is a problem, and what was called the mass discrepancy in several systems, ranging from the scale of galaxies up to the scale of clusters of galaxies. Then there is a second phase where people realized basically that the mass discrepancy problem could be solved in a sort of a general paradigm in which there's a lot of dark matter out there. And then there is this third point, which is still a completely new and interesting point per se, where people realized that all the matter that was out there was not in the form of dim stars or machos, massive compact objects in the halos and so on, but it was really in the form of something really very different from standard, from the atomic matter, baryonic matter we're familiar with. So, for those of you who are interested, we organized in June of this year a workshop in Amsterdam with some of the pioneers of the field. We had Albert Bosma, who was one of the pioneers in rotation curves, and then people I'm sure all of you are familiar with, people, Sadone, Sil, Turner, and White. And the videos of all these lectures will be online soon, so if you want to know more about the interesting history of this field, please take a look at this slide. Now, let me ask the question, let me just go and discuss now the central topic of my review talk, which is dark matter searches. As I said, in order to search for something, you need to have an idea. If you want to build an experiment to search for a particle, you need to have an idea about what this particle would look like, whether it is an axion with milli-electron volt mass, or whether it is a new particle at the Wisk scale. You would build different experiments for that. And since one of the authors of this review article is here, Marco D'Aoso is one of the authors of this review paper we've written a few years ago. You can ask the question, what do we know already about the dark matter particles? What are the constraints on dark matter particles? And that's particularly useful if you have friends among particle theorists who come up always with very interesting ideas about what dark matter could be. And so this is basically a 10-point test that you can give them. So if you have a new particle, a new theory that predicts the existence of new particles, this particle has to pass a number of tests. And let me mention at least a couple of them. Maybe first and foremost, this particle has to pass a stringent constraint on the abundance of this particle in the universe. We know the abundance of dark matter with a few percent accuracy these days, thanks to cosmic microwave background experiments. We know that dark matter must be cold, and we can actually quantify this, the term cold. We can set a constraint on the free streaming scale of dark matter particles. We can set a constraint on the charge. We know that its coupling must be such that it's compatible with Big Bang nucleosynthesis and with the structure and evolution of stars. And then we can set a constraint on the couplings of this particle with itself through observations like the bullet cluster. So we know that it's close to collisionless, not in the self-interaction is not necessarily zero, but it must be relatively small. We know that the couplings with ordinary matter must be small, and we actually have interesting constraints on this scattering cross-section between dark matter particles and baryons. And then we know also something about the fact that these particles should not annihilate, self-annihilate, or decay too much, otherwise they would produce gamma rays, synchrotron emission, neutrinos, or fluxes that we have not detected. And then you want that this particle, at least in principle, should be detectable. So there must be at least a thought experiment that you can perform in order for this particle to be viable. Otherwise, it's kind of easy to hide a particle in a sector of the parameter space where this particle, for instance, interacts only gravitationally with ordinary matter and doesn't do anything else but producing mass in the sky. So what's interesting is that we talk about dark matter searches, but if you follow newspapers, dark matter has been discovered many times already. So this is just taking one particular website. This is the Guardian. That is, if you look at the titles, the dark matter finally being detected in 2009. New light cast on dark matter 2013. And in 2014, we had two discoveries of dark matter, one in the form of a 40 GeV. Actually, there were two discoveries in these articles. One, a 40 GeV WIMP in Fermi data, and a 70 eV Serrano neutrino from detection from Chandra and XMM. And then there was an even more recent claim of detection with XMM data, a background fluid looking through the magnetic field. So yeah, so at least this tells us that we should be careful when interpreting results and before making press releases. Let me, since I want to talk about real experiments that are going on, and at least I want to mention at least one interesting result in each of these detection strategies. Let me tell you briefly how we arrange typically dark matter particles in the field. I would say that a large fraction of the community focuses on the possibility that dark matter is in the form of WIMPs. So basically there is a connection between the weak scale in particle physics and dark matter on cosmological scales. So WIMP stands for weakly interacting massive particles, and there are natural candidates that arise naturally from theory like symmetry or theories that that try to extend the standard model of particle physics to explain some of the fundamental problems of the standard model, like the hierarchy problem, the fundamental distinction between bosons and fermions, and so on. You can also follow a different approach. Instead of trying to solve the big problems in physics, you can try in particle physics. You can just extend the standard model with particles that have weak interactions at the weak scale, and then just work with them. So this is a minimal approach to dark matter. But there are many other possibilities that have been discussed in the literature. And actually, it's a bit unfair to just divide the candidates, in just these two ways. But probably this reflects, the fraction of the community that is working on these different candidates. Let me mention at least that there are candidates like axioms and sterile neutrinos that are, perfectly viable dark matter candidate, and they are, very well motivated from a theory point of view. So we'll do my best to discuss the dark matter problem and dark matter searches, but keep in mind that there are many other talks about dark matter at this conference. So I've written a few names of people who will give talks in the plenary session. So consider this talk as basically an introduction to what will be discussed in the remainder of this conference. All right, so let's discuss dark matter searches. As you know, there are at least 3 different strategies if you want to detect the particle nature of dark matter. There are collider searches that are these days performed at the Large Hadron Collider. There's indirect detection, which is based on the search for the secondary particles producing annihilation or decay of dark matter particles, and then there is direct detection that seeks to really detect the interaction of dark matter particles which are Fermi. Now, in the basics of indirect detection, I'm sure that many of you are familiar with this. The idea is quite simple, actually. It has been proposed back in the 80s. The idea is that In the early universe, in the case of, if we just focus on WIMPs now, these particles are kept in thermodynamical equilibrium with particles of the standard model through annihilation process of this type, and where this annihilation can happen in many different ways. It really depends on what happens to your particular particle physics model. But basically, the bottom line is that dark matter particles annihilate particles of the standard model and vice versa, and this reaction is in equilibrium. And the reaction is in equilibrium until the interaction rate drops below the expansion rate of the universe. So basically, at some point, the density of these particles, and this is the equation, the Boltzmann equation that describes the evolution of the density of the universe in an expanding universe, is regulated by the annihilation cross-section of these particles. And as it is well known, for an annihilation cross-section which is at the weak state, so if you put 10 to the minus 26 in this unit, centimeters cubed seconds minus 1 in this formula, you get an omega h squared, which is about the 0.1, which is precisely the value which is observed for dark matter. So what this is telling you is basically that at some point, after the initial phase of equilibrium, at some point the density of dark matter particles, so the number of particles basically remains frozen, it just remains constant throughout the history of the universe, and therefore the number density just gets diluted by the expansion of the universe, the physical number density. However, as you know, these annihilation processes do not depend on the average density in the universe, but they depend on the density squared. In particular, if you go in structures which are very dense, we know we do not live in a uniform universe. There are many very large overdensities. In the solar neighborhood, the local dark matter density is about a factor of 10 to the 5, I think, larger than the average density of the universe. And if you go towards the center of the galaxy, this density will be even larger. So you can make use of the fact that this annihilation process can happen at a large rate, a potentially large rate, at the center of structures, and you can calculate what would be the flux of secondary particles produced in these annihilation processes. In particular, if you think about photons, which is maybe the easiest example to visualize, you can calculate what is the flux of photons produced, for instance, at the center of the galaxy at a given energy, and you can easily express this in a very simple way. We have a prefactor that depends on the particle physics of your dark matter particle model. You will have a first factor that depends on the number of photons you produce per annihilation. And this comes directly from the type of particle you have in mind. Once you write down your dark matter model, you know what these particles annihilate to, so you can calculate what are the final products of annihilation, in particular the number of photons produced by this annihilation. And then you have an annihilation cross-section that is more or less set by this argument, at least if you want to do things in a model-independent way. You can just take an annihilation cross-section that gives you the correct relief density. Then you have to specify the mass of the dark matter particle. And the reason why this depends on the mass of the dark matter particle is that, we just say that the annihilation rate depends on the number density squared. The rate of annihilation really depends on how many dark matter particles you have there. But the constraint that you have from an observational point of view, just by looking at the dynamics of galaxies, is on the mass density of these particles. So what you want to do is basically integrate over all annihilations happening between you and the target you're observing, for instance, the galactic center. So you integrate this density squared, this mass density squared, and you divide this by the mass of the particle squared. So this quantity here only depends on the distribution of dark matter in your galaxy. So for instance, if you think about the Milky Way, the galaxy we live in, you think about the galactic center, this really depends on how dark matter is distributed, not just how much dark matter there is, but how dark matter is distributed between yourself and the center of the galaxy. And to update this to what is going on now in this field, let me mention that, I want to mention two things. One is that we're making progress on numerical simulations that describe how dark matter is distributed in the Milky Way, until we're making progress on observations, observations on what really the local density of dark matter is. So let me describe this in a bit more detail. What I'm showing here is one of the most recent simulations, which is the Illustris simulation. And I think the interesting aspect of, I will not discuss too much what's in this simulation. I would just refer you can check the website. They have many, they have full references on papers written by the collaboration, and actually very beautiful images and videos. But basically what's happening is that, we are, as a community, we are learning how to put variance in these simulations. And in particular, we are learning how to produce in these simulations that historically were, dark matter only simulations, until very recently. We're learning how to produce realistic galaxies. And in particular, we're learning how to describe processes like supernova feedback and feedback from AGNs and star formation and so on. This is still done at a subgrid level, in the sense that we really do not simulate the formation of stars and the explosion of supernovas in these simulations. But we're learning to produce galaxies that really look like the galaxies, for instance, the galaxy we live in. And I refer you to this website for more information about the simulations. We're also making progress from an observational point of view, in the sense of trying to figure out what really observations about the dynamics of the galaxy tells us about how matter is distributed in the galaxy. And this is a recent result. This is just actually some preliminary results that we have obtained in collaborations with Fabio Iocco and Miguel Pato. What you see here is the angular circular velocity. This is the rotation curve, basically, of the galaxy, of the Milky Way. And what you see, so this is as a function of the galactocentric distance. We are right here, 8 kiloparsec from about 8 kiloparsec from the center. And what you see here is data. So this all these red points are data, different sets of data. Actually, it's a compilation of many data of different types with the corresponding error bars. And what you see here in this shaded region is actually the rotation curve that you would predict from baryonic models of how stars and gas are distributed in the galaxy. Okay, so this is the gray region actually includes about 70 different baryonic models that are available on the market that describe how stars and gas are distributed in the galaxy. And this is the rotation curve that you can reconstruct directly from those data. And what you see basically is, if you just focus on one of those, which is one of the models that actually fits best the distribution of star and gas, you can ask what is the residual in the rotation curve. You see that the data are systematically above, at least at large distances, are above these baryonic models. You can ask, you can plot the residuals on top of this black line. And you see that there's a trend. They remain always above the predicted rotation curve, basically everywhere. And what I want to show you is that I want to draw your attention to this dashed blue curve that seems to go through the data. This is just a vanilla Navarro-Franken-White model. So this is a profile with r to the -1 in the inner parts, r to the -3 in the outer parts, which is not fit to the data. This is just, if you just open up an article on dark matter and take, 0.3 GeV per centimeter cube as the local density and 20 kiloparsecs as the scale radius, this is what you get. And basically, without any fit, it seems that this profile can go through all the data in a very simple way. So it seems that really the NFW is really capturing something about how matter is distributed in the galaxy. And if you ask what is the evidence for an additional component based only on rotation curve data, this is the reduced chi-square that you get. And the reduced chi-square has been computed for each of the 70 models, baryonic models that have been plotted in this, that are included in this gray region. You see that basically they go above the 5 sigma line at galactocentric radii, which are always below 8 kiloparsecs. So what this is telling you is really that, from the data directly is emerging the evidence for dark matter even in the inner regions of the galaxy, not just in the outer parts where we know the gravitational potential is dominated by dark matter, but it's really coming out naturally from the data even in the innermost region of the galaxy. Okay, so what you can do is you can predict an annihilation plot. So you can, for instance, take a numerical simulation, put an observer in it, 8 kiloparsecs from the center. Then you start to shoot sight lines in different directions, and then you can calculate what is the predicted number of photons that you should detect in different directions of the sky. So in particular, if you plot a map, if you plot this in galactic coordinates, what you will find is that there is a prominent region towards the center of the galaxy, so a bright spot, which is where the density, dark matter density peaks in our galaxy. And then you see a number of substructures throughout the galaxy that correspond to smaller halos. It's quite tricky actually to implement all the halos. Numerical simulations resolve halos down to 10 to the 4, 10 to the 5 solar masses. So for the rest of the subhalos, you have to do things in a careful way. We can discuss this if you're interested. But basically, this is what you would predict from numerical simulations. And this is actually what you predict for any dark matter particle that self-annihilates in the galaxy. So this, the different types of dark matter would just, scale the flux up and down. So this would scale I think it would change the normalization of the scale, but you always predict something which is, strong in the galactic center and then a number of substructures. So you can compare this with observations. This is the predicted annihilation signal. You can compare this with observations, and this is in the same coordinates. So this is again in galactic diffuse sky in galactic coordinates with the galactic center at the center of the image. And what you see, of course, is that this emission is very different from the predicted emission because there are, very strong astrophysical emission. There's a very strong astrophysical emission coming from, especially from the disk of the galaxy. Plus, there are many, many sources that are scattered around all around the sky. There are galactic sources, there are extragalactic sources, and so on. So the game here is to try and understand and possibly subtract this very strong foreground and trying to detect the emission that lies behind, basically. So if you just do as an exercise, just I invite you to take a look at these two substructures here, for instance, and the galactic center here. What you can do is to start from your predicted signal and divide. Your predicted signal is a number of photons per pixel in your map, basically. You can just divide that if you want to get an idea of what is the most interesting region to search for dark matter. You can divide this predicted signal, predicted number of photons, by the square root of this map, which is your background, your noise, basically, and you get a sensitivity map. And the sensitivity map tells you that despite the fact that the galactic center is so so crowded with this very strong foreground astrophysical emission, still in most cases you get that this is the region with the largest signal to noise. And then you have the two sources, the two substructures that I was referring to here and here, plus a number of others. So this is in general what the expectation for when you do indirect detection studies. Typically you expect that there is a signal at the galactic center that would be difficult to discover because of the presence of astrophysical foregrounds and the number of substructures available. And this is the most interesting result in the field has been the discovery of this excess emission towards the center of the galaxy. It was actually claimed a number of times throughout the years. Then, maybe the most interesting article that established the case for this excess emission, the most important one maybe recently was this article that appeared in February of this year. And what you see here is basically similar to what we were seeing before. So this is the total flux. These are data, Fermi data. This is the total flux, number of photons towards the center of the galaxy. You see that we are looking at a relatively small window towards the center of the galaxy, a few degrees around the center, in different rows of different energy bins. And what you see is basically that if you remove the astrophysical foreground from the observed image, they actually have to model the astrophysical foreground. It's not an easy procedure, but if you remove that, you end up with a residual emission in each of these three energy bins. So the authors of this paper, they've tried to calculate the spectrum of this emission, and what they've shown, and here you see it is the E squared times the NDE, so the energy spectrum multiplied times E squared, and these are the data, the data point you see here, and what you see is a dark matter model. So I think this is a dark matter particle annihilating to maybe BB bar, but anyway, just a relatively standard annihilation channel. And the claim that was made in that paper is that, well, first of all, that there is an excess, and that it is quite difficult to explain this excess in terms of known astrophysical sources. In particular, if you consider millisecond pulsars that have been considered to be one of the major potential sources contributing to the flux at the galactic center, at these energies, you see that if you look, for instance, at the dashed line, this is the spectrum of all millisecond pulsars observed by Fermi, and then you have three globular clusters whose emission is believed to be dominated by millisecond pulsars. So the argument here is that the spectrum of millisecond pulsars fails to reproduce the flux at small energies around 1 G. It is still hard. And let me also mention that another paper came out. So part of the skepticism about this claim was due to the fact that a particular model was assumed for the diffuse astrophysical emission. And this article by Cristo Beniger and Francesca Calore, that was like two months ago, they did a very thorough analysis, and I think they demonstrated in a very convincing way that no matter what kind of model you assume for the astrophysical emission, you always get some excess. So I think we are converging towards a situation where there is a sort of an excess towards the galactic center on top of the physical models that people are building using Galprov and so on, and we need to understand what that is. What in the paper of Dalen and Kahn in February, they've also shown that the angular decline of this flux away from the galactic center, so there is a flux as a function of the angle away from the galactic center, faults like an angular decline, which is very similar to the one predicted by these very steep dark matter profiles. So if you take, actually you need something a bit steeper than NFW, which is order -1 in the other parts. You need something like between 1.2 and 1.4 to fit this data. But this is something that is not unconceivable from the point of view of dark matter density. So the claim was that this makes it a very strong candidate for a dark matter emission towards the galactic center. And this is an interpretation in terms of annihilation cross-section and mass, again from the paper of Calore and Beniger, where basically they've tried to estimate the cell 95% contours of the BB bar, assuming a BB bar annihilation channel and a tau annihilation channel, and you see what are the most probable regions in this parameter space that would explain the excess at the galactic center. So I think the reason why this has attracted so much interest is that you basically naturally achieve masses and cross sections which are typical for WIMPs. The signal is spherically symmetric. The angular decline is reasonably in agreement with what one would predict for the galactic center. let me mention two things. One is that Christoph Henniger is also here at this conference, sitting right there, and he's giving a talk on this on Friday. So, if you want to know more about how the analysis is performed, what are the possible astrophysical foregrounds and so on, feel free to ask him questions. And let me also mention that this GeV excess was, everybody was sort of waiting for the Fermi collaboration to make a claim about the existence of an excess towards the galactic center. And there was this meeting last month in Japan at the Fermi Symposium, and I think possibly for the first time, they made a statement where they basically confirmed the existence of an excess, and they also argued that among the attempts they made to explain this emission, peak profile like an NFW provided the largest improvement in the fit to the data. Okay, so this is something worth keeping an eye on. For the purpose of this particular talk, the question I want to ask is what we learned from this. We have this emission from the galactic center that can be explained potentially in terms of dark matter. The question is, how do we convince ourselves that there is something interesting going on right there? How do we make sure that astrophysics is not responsible for this emission? We live in an era where it's easier to make a prediction for supersymmetric the spectrum produced for a supersymmetric neutralino than it is for astrophysical sources. Okay, so it's very hard to rule out in general an astrophysical interpretation of the data. And in general, there is always this problem that dark matter always can explain an excess, especially with this particular shape, with this bump shape towards the center of the galaxy, or in any other astrophysical environment. You actually have a lot of freedom in energy. If you adjust the mass of the dark matter particle from the MeV scale all the way to the TeV scale or multi-TeV scale, you can move this predicted annihilation flux left and right. You can adjust by changing the profile. You can adjust the normalization, and by varying the annihilation cross-section. And if you vary the annihilation channel, you can even adjust the shape of the excess. And if you're dealing with antimatter searches, you can even vary the propagation parameters, for instance. So in many cases, the inverse problem of going from the data to an explanation will admit a solution in terms of a dark matter particle, but this also reflects the fact that we don't know much about dark matter particles, so we can vary the parameters a lot. So how do we convince ourselves that we found dark matter? Well, one obvious thing that we should try and do is to search for the similar type of emission from other astrophysical objects. And in particular, as I was arguing before, we need to compare with dwarf galaxies, the substructures in the Milky Way. And this is one of the many articles that have been written in the last few weeks and months about this, about the GeV excess in general. What these authors did was basically to calculate the exclusion plot coming from dwarf galaxies. So basically, the fact that we do not see an excess emission from from dwarf galaxies allows you to set constraints in the parameter space sigma b, the initial cross section versus mass. And this is the constraint they get. This is the main result with the associated uncertainty. This is the thermal cross section that you see here, and this is a more refined version of an annihilation, of the thermal cross section. And this is one of the regions. I think this is taken directly from the Daylan et al. Paper, where these parts were annihilated into BB bar would produce a good fit with data from the galactic center. So the data, so the exclusion plot is getting very close to the region preferred from the data, based on the data from the galactic center. So this is an extrapolation about what can be done in the future. So I guess there is a potential to discover something. It's unclear whether the answer would be conclusive. So for instance, if you if you don't see anything at all, I think there are always ways to argue that the signal at the galactic center, the profile is more peaked there than it is in both galaxies and so on. But if you do see a signal also from there, and if the signal has the same energy spectrum, then this will be make a very convincing case for an annihilation signal, dark matter annihilation signal. So let me summarize the situation with this list of pros and cons of indirect detection. Among the pros, there is no need to do dedicated observations. Especially Fermi works in survey mode, so you don't need to apply full time for these telescopes. You can always cross-check the results with other targets, other wavelengths, other messengers, and it's really never boring. There are hints of discovery all the time, so it's an interesting field to work in. Among the cons, there are the orders of magnitude uncertainties on rates. It's always hard and sometimes impossible, based on single observations, to exclude the astrophysical interpretation of data. And in general, you need to combine this information from indirect searches with other strategies if you want to obtain incontrovertible evidence. So let me move quickly to direct detection and accelerator searches. The idea is, I guess, familiar. The idea of direct detection, I guess, it's familiar with all of you. You build a big experiment, you place it underground to shield it from cosmic rays, and then you wait for dark matter particles to interact with your detector, and you measure the recoil energy of the nuclei struck by dark matter particles. And there are different ways of, different technologies to do that. The rays, so we've seen the annihilation flux that depends on particle physics and in astrophysics. The rate of events in a direct detection experiment also exhibits the same type of dependence on astrophysical and particle physics parameters. Typically, you have the local density of dark matter in front of the ray, the mass of the dark matter particle, and the mass of the nucleus in your detector. Then you have an integral over the velocity distribution of dark matter particles. And then you have a differential cross-section that describes the interaction of the dark matter particle with the nuclei and nucleons and nuclei in your detector. So the status is that the leading experiment in the field, the one with the best sensitivity, is LUX currently. And the way these experiments work is basically like this. You build, there are different types of experiments. The ones I'm showing you are the xenon experiments. Other noble liquids like argon would work the same way. You have a liquid xenon in the bottom of the experiment, and then a thin layer of gas in the upper part. So what you observe is basically when you have particles entering your detector, if it is things like electrons or gammas, they would recoil on electrons, and they would produce first an ionization signal that is observed by the experiment, and then another proportional scintillation signal, as it is called, when these particles are drifted above the liquid xenon and go to the gas. So by comparing this is another case where you interact with the nucleon. So again you get an ionization signal, which is in this case much smaller than in the previous case. And then you get the proportional signal is smaller because you get fewer electrons ionized in each of these events. So the bottom line is that by looking event by event at what goes on in the experiment, you can figure out what kind of particles are entering in your detector. And if you have a model for the flux of neutrons entering in your detector, these experiments are also self-shielding, so there's a lot of interesting technology in them. Then you can figure out whether dark matter is made of wind, or whether you have a dark matter signal in there or not. And just to show you that these things are going on and becoming even more interesting, this is a video that I took actually last week. It was 3 weeks ago at Gran Sasso, from inside the Xenon 1-ton experiment. We are inside the water tank that is obviously not filled yet, and this overlap is showing us the experiments. I see some people in the room were at the same event actually here, and what you've seen above us was the vessel where the Xenon will be, which is about this big. Okay, so this will be filled with Xenon. Do I have 5 more minutes? Yep. So let me go quickly through the main results here. Xenon, this is the plane scattering cross-section versus mass. And this is the result that Lux has obtained. This is an exclusion plot. No events above the background have been observed. So we can rule out cross-sections above this line. And just notice the order of magnitude of these cross-sections. We are talking about 10 to the minus 45 centimeters squared. Okay, so 10 to the minus 21 barns, if you're more used to this type of unit. These are really fantastic sensitivities. So incredible that soon, well, or at least in the next decade or so, you will hit a floor of neutrinos produced by the sun that will produce coherent scattering in your experiment. Okay, let me just say this final slide about the red detection. The pros of this strategy is the possibility to cross-check with other experiments and targets. The dependence on astrophysical parameters is weaker. We don't have this dependence on the integral of rho squared that was leading to orders of magnitude uncertainties in the previous case. And you have the possibility to measure the dark matter mass, quite accurately if it's below 100 GeV. If it's above 100 GeV, you can probably set only a lower limit on the mass. And then you have cons, which are, the fact that you need to build dedicated experiments, it's hard to exclude unknown and modulating backgrounds in some of the experiments that search for modulation of the signal. And it only constrains the product of cross-sections times local density. So if you find a particle with these experiments, you will know it contributes to dark matter. But to find out how much it contributes to dark matter, whether all of it or 1% of it, it's going to be basically impossible because these two quantities are completely degenerate. Now, in the last few minutes, let me just comment on dark matter searches at the LHC. You're all familiar with the Large Hadron Collider, 27 kilometers ring, and there are two experiments, Atlas and CMS, which are particularly relevant for this type of searches. When people think about extensions of the standard model, they often have, at least in the case of WIMPs, they often have a picture like this in mind. This is what is relevant, for instance, for supersymmetry searches. You have all the known particles of the standard model on the bottom part of this plot. And then in blue, you have, for example, the supersymmetric partners, as they would be called in the supersymmetry jargon, basically a new hierarchy of particles of new physics. And the idea here is that when you smash protons together in big colliders, you can produce heavy particles, scalar particles like the partners of the quarks, for instance. And by following the decay of these particles from these heavy superpartners all the way to the lightest particle, which is often to be found among the partners of the gauge bosons, this is where the neutralino lies in supersymmetry. By following this decay chain, you detect all the particles of the standard model that are produced, and then you have a fraction of the energy that is carried away from your detector, and you detect these new particles through an imbalance in the energy reconstructed, like this way. So among the pros and cons, well, there's no dependence on astrophysics. The backgrounds and the systematics are under control. This is really, precision particle physics. They will be performed no matter what. We have in 2015 a new run of the LHC starting, so this will happen. And this allows measurements of mass and couplings of these new physics particles. Among the cons, there is the fact that it's often hard to identify new particles with dark matter in a model-independent way. You have to specify a model, and sometimes even if you specify a model, it's hard to do this reconstruction in a precise way. And you need complementary information from astroparticle experiments. If I can use 1 minute, is it okay? 30 seconds? 30 seconds, okay. All right, you can do this in a very effective way, and the conclusions are that so there's a huge theoretical and experimental effort towards the identification of dark matter. Each of these detection strategies have their pros and their cons, but it's becoming quite clear that if you want to reconstruct the properties of dark matter, if you want to identify dark matter in a convincing way, you probably need a combination of all these approaches. While I take questions, I'll maybe just flash this advertising. We're hiring PhDs and postdocs in Amsterdam, so if you're interested, or if you know people who might be interested, please refer them to this website. Thanks a lot.
Time for a couple of questions.
symposium was not the first place where we acknowledge the GDSS. We already published it in 2009. But why we are so high about claiming memory dark matter discovery in the galactic center? It is very simple. If you look just at the instrument response function, at the angular distribution of converting at altitude UD, you have 2 degrees. So 2 degrees means this means that if you have just a point source, 78% of the photons coming from the source are actually outside this 2 degrees. So this means that the galactic center, there is a very crowded region, actually is really very, very difficult to discriminate these models. And actually, that's why, and this is an intrinsic problem, because it does depend on the nuclear scattering and the converter of the detector. So that's why we are now excellently to address the galactic center problem, and we are thinking of a new instrument, and we are applying for this M4 medium mission of ESA, and we'll talk about this in this meeting.
Excellent. No, absolutely. And I didn't. What I meant to say is that maybe a sort of a consensus, as far as I could judge from outside the collaboration, of course, is emerging that this is something interesting, and present this claim about this NFW that fits, that is among the possibilities, this is one that fits best the emission. I think this is the first time that it was made.
No,
it wasn't. Yeah. Okay.
Already in 2009, we actually was the first that we discovered the excess in the region between 2 and 5 GG. So we knew about this excess.
I think there will be a dedicated discussion on. I think there will be a dedicated discussion on. Yeah.
I think you forget to mention in the list of evidence for the discovery of that matter the recent announcement for the 70G of the AIS2 results. Maybe you can add to the list. The comment that I want to make
in the news, yeah, sure.
The comment I want to make is that we all know where to look for that matter indirectly in research. Now the question is on the sensitivity that we can get from certain values. I think without the true frequency search for indirect searches, we still might be stuck with one of the issues like I mentioned about the difficulties of dealing with one single experiment and subtraction of sequence and comparing values. So I believe that I don't agree. The only way we can convince ourselves is to look for the best cases and to look for the new.
Absolutely, yeah. So I absolutely agree with you, and I briefly mentioned this in the presentation. It's that we really need to, if all we have is indirect detection and there's no hint of discovery from direct detection of or accelerators, because it's quite clear that if you have a hint like the one we have towards the galactic center, and then you find a neutralino with a mass of 55 GeV in the LHC, then you can build a consistent picture. Of course, if all you have is astrophysical data, it becomes much more complicated, and doing multi-target, multi-wavelength is absolutely the way to go.
One last question.
Let me try to have a little bit different look on the issue of the indirect detection. I learned in my old particle physics training that if you have some physics, known physics, as astrophysics, that's your background, and you have to estimate your background with uncertainties, and of course you can do cuts and so on, and then you have to evaluate what are your chances of seeing a signal. For example, QCD is also very complicated. Not only astrophysics is complicated, we will say, okay, we need a certain conservative estimate on the rate of QCD effects, and then we try to find a signal that sticks out. Here, my feeling is often that it's a bit different. You deal, with dark matter and astrophysics with two, equal-footing physics candidates, which in a certain sense is not what, we do as a particle physicist. We would really say, we have an astrophysical background which is poorly known, and that is a big systematic error, and if you have no signal sticking out of it, how can we finally believe?
No, that's exactly what's happening in the community right now. So, for instance, you will see in the presentation of Christoph Weniger on Friday, that they've done precisely that. So they've taken physical models of the background, and they've assessed that on top of what is known in the galaxy, there is an excess. The difference with respect to what you're referring to, hold on. Systematics are included. That's precisely the goal of their paper. The assessment of systematics is precisely the goal of that paper. However, the problem is that in QCD, you have a standard model of particle physics that allows you to make predictions. You don't have a standard model of astrophysics. If there are unknown astrophysical sources, or if the spectrum of these millisecond pulses depends on their location in the galaxy, how would you figure out?
We have a model which is just standard Ariane physics. It's just difficult to compute. The same is true for many aspects of QCD. So in QCD we can by far not compute everything, but we just say in the regions where we know pure polygon will come out from QCD, it's a bad signal, it's a bad region for getting signals.
There is no standard astrophysical model. I mean, you cannot compute, the same way you compute complicated things in QCD, you cannot compute the behavior of a star with a magnetic field around it. I mean, there's no calculation about that. I mean, you're welcome to try and do this, but that's precisely the problem.
Yeah, but it's not the same problem. I mean, you have a theory behind, which is known, and then a very complex situation, which is...
We don't know how to deal with those complex situations. I mean, the degree of complexity in QCD is not the same as in weather, in climate science, right? You can also say, in climate science, we know the Brionic model, we should be able to make predictions. It's just a complicated system.
That we can think uncertainty, that is what I want to say. So if you find some cards and so on, to reduce the uncertainty, fine. But as long as you say there's a big uncertainty, we do not really know.
I encourage you to go to the talk of Christoph Weniger, where exactly the problem of assessing systematics in particular is discussed. There's a lot going on in it.
We're going to break for tea. I'm sure there'll be discussions during the tea break. We'll all be back at 11:30.